Let's delve into the intricacies of sizing feeders for continuous and non-continuous loads, a critical aspect of electrical installations governed by the National Electrical Code. The question at hand concerns the apparent conflict between Article 220, which dictates how to compute total load, and Articles 215.2a and 230.42a, which mandate specific sizing requirements for feeders and serve as conductors based on continuous and non-continuous loads. Article 220 provides the rules for calculating the total load. It's essential to recognize that these rules, while comprehensive, don't explicitly incorporate a mandatory 25% increase for continuous loads in all instances. For example, Section 220.15 might state that electric heaters are computed at 100% of their connected load, even though they often operate continuously. However, Articles 215.2a and 230.42a introduce a seemingly contradictory requirement. These articles stipulate that feeders and service conductors must be sized to accommodate the sum of the non-continuous loads plus 125% of the continuous loads. This means that continuous loads, those operating for 3 hours or more at a time, are effectively derated when it comes to conductor sizing. The core question, therefore, is whether the load computed according to Article 220 takes precedence over the sizing mandates of Articles 215 and 230. The answer lies in understanding the intent and application of each set of rules. Article 220's role is to determine the minimum load that a building or system is expected to draw. It provides a standardized method for adding up all the various loads, both continuous and non-continuous. The calculations within Article 220 factor in demand factors and other allowances to arrive at a realistic estimate of the total load. Articles 215.2a and 230.42 address the capacity of the conductors themselves. They ensure that the conductors are adequately sized to handle the expected load, with a safety margin built in for continuous loads. This 25% increase for continuous loads isn't an additional load being added to the calculation, it's a requirement to select conductors with sufficient ampacity to avoid overheating and potential hazards when supplying loads that operate continuously for extended periods. Therefore, the load calculated under Article 220 does not negate the requirements of Articles 215 and 230. Instead, the load derived from Article 220 becomes the foundation for applying the conductor sizing rules in Articles 215 and 230. You first compute the total load, identifying which portions are continuous and which are non-continuous. Then, you apply the 125% factor to the continuous load portion before summing it with the non-continuous load. This adjusted total load is then used to select the appropriate conductor size based on its ampacity rating, referencing tables like those found in Article 310. In essence, Article 220 calculates the load, while Articles 215 and 230 ensure the wiring is appropriately sized to handle that load safely, especially when continuous operation is involved. Seemingly conflicting rules work in tandem to achieve a safe and reliable electrical installation. For instance, consider a situation where Article 220 dictates a total load of 100 amps, with 60 amps being continuous and 40 amps being non-continuous. Following Articles 215 and 230, you would calculate 125% of the 60 amps continuous load, resulting in 75 amps. You would then add the 75 amps to the 40 amps of non-continuous load, arriving at a total of 115 amps. Therefore, you would need to select conductors with an ampacity of at least 115 amps, even though the initial calculation under Article 220 yielded only 100 amps. This illustrates that the 125% factor is not adding more load, but is a method of derating the conductor's ability to dissipate heat when dealing with continuous loads. This ensures a safer and more reliable electrical system, reducing the risk of conductor failure and potential fire hazards.